Okay, so hello everyone. I'm Martin, and I'm going to talk a little bit about llvm-mingw. Like everybody else here today, first I'm going to talk a little bit about the history, about how things became what they are. And then I'm going to talk a little bit of what I promised about how to do quality assurance of a toolchain on a zero budget. So first off, what is llvm-mingw? It's a mingw based toolchain targeting Windows, based entirely on LLVM components. That is, it's a toolchain which is freely redistributable, properly licensed open source, and instead of the GCC, GNU linker, those components, we are using the LLVM corresponding tools for everything. Everything is replaced and it works quite well. So the origin story, how did I end up doing this? I have a background in a lot of multimedia projects, working on ffmpeg, VLC, and so on. I have been porting ffmpeg to many odd mobile platforms since 2006, Symbian, Windows CE, and these kind of things. And in 2014, VLC had the goal of to port VLC to Windows Phone. Windows Phone was a thing in 2014. But the VLC is very heavily tied to being built with mingw build tools. It consists of around 100 third-party libraries. Most of them are built with auto tools, and building this with MSVC is not really something you want to do. You primarily cross-compile VLC for Windows from Unix. But in the upstream GCC tools that they were using, there was no support for anything else than Windows on x86. They tried to involve a GCC maintainer to develop something. There was like a couple patches, but they never went anywhere and so on. So what do you do? I gave them a proof of concept. You can take the MSVC compiler, wrap it in a shell script, have the shell script interpret GCC style command line parameters, remap them to what MSVC takes, and so on. And I made a proof of concept that was enough to build a trivial small library. Gave it to them, see, it works, you can use this, and they had to complete it to make it not just build one trivial library, but all the 100 of them that they are including. So they did ship VLC for Windows Phone, built this way. Building it was slow and painful. I'm told, I never tried it myself, and so on. And also cross-compilation is tricky. So there was a demand of, there has to be a better way of doing this. And then at some point, somebody realized that llvm actually has some sort of support for targeting Windows on ARM. llvm also had some set of support for targeting mingw on x86 if you happen to have an existing GCC-based toolchain targeting x86. So you could swap in the compiler, and that's it. Linker, runtimes, everything was still what you used to have. So there was some initial efforts by Martel Malone, starting around 2015 up until 2017. I got involved in this and heard about it and tried to play with it in 2016 and so on. It was progressing, but slowly. Then in 2017, there was a different side project coming up. There were lots of rumors about Windows coming to ARM64. These rumors were entirely unsubstantiated, of course, but there was the buzz about this. The Windows SDK had a handful of executables for Windows on ARM64. There were no compiler for it. There was, of course, no operating system where you could run them, but there was this small set of mythical executables. So then Andre, at this time, added some patches to Wine, so it could load and execute these binaries. Well, most of them crashed. But out of the dozen or so, I think one of them actually didn't crash. So that was nice. So I tried to looking into the other ones, what's going wrong, what's crashing in the other ones, and most of the traces pointed towards printf. So I realized that it seems that Windows on ARM64 has a different calling convention for variable argument functions. This is also the case on Windows on x86-64, and I tried hacking around this by adding inline assembly and whatever in the Wine code, but quickly realized that it's not really possible to work around this on the Wine side. You need to have the compiler to be able to tag that this function has a different calling convention. And as I happen to have at least checked out llvm once before, I was kind of familiar with the code and, well, tried hacking around to see how hard could it be. It turns out that an afternoon of hacking, and then you have the printfs working. At least some of them. I mean, the patch wasn't right, but it was in the right direction at least. So with this in place, I had something of a test environment. I had Wine running on Linux on ARM64, where I could execute this handful of binaries. Some of them still failed, but some of them worked. There were also other issues like the x18 register, as we've been discussing before. That's not interesting in this case, though. But then at the same time, some guy from Qualcomm also contributed some initial patches to llvm for writing COF ARM64 object files. So it wasn't a complete compiler, but like the initial commits. And the Windows SDK, it both had executables that you could run there, but it also had the import libraries and everything else. The MSVC tools didn't have their libraries, so you didn't have the high-level msvcrt.lib or those kind of things, but the Win SDK parts were there. So I tried playing with this. Can I improve the code generation and add support for this in the linker in llvm so I can produce new binaries that will run on my Wine on ARM64? And it turns out, yeah, it's not so hard. A couple of weeks of hacking around, and then I have working both trivial executables and slightly less trivial ones based on a hacked up Windows SDK. Well, hacking up the Windows SDK is not so fun, so as I had this parallel track on playing with MingW, I tried to fold the ARM64 track into this, so added initial support for ARM64 in MingW, which required a lot of deduplicating files. They had duplicated dev files listing all the symbols in all the DLLs for x86 32-bit, 64-bit, and ARM32 so far. And my attempt was just take the ARM32 or whatever and copy it over, and then when we know better, we'll apply some diffs. But they don't want to duplicate those first. My first job there was to deduplicate the existing files, then copy the shared ones over for ARM64 and use them. And I ventured out on a little small side quest as well here to add UCRT support in MingW. Because if you're targeting ARM64, which was then on Windows 10 and so on, there's no real reason for you to target anything older than the old MSVCRT DLL hacks. So we can do UCRT here, and everybody else can use it as well. So that was a small side product of this venture. So by the end of 2017, I had a seemingly working toolchain. I had managed to get lib-on-wine, libc++, and those parts working. A toolchain that can build binaries for ARM64, validated on my Wine setup. The most important part by Martel Malone was the MingW linker interface. So when you're invoking the linker in the GCC style environment, you're passing arguments in one way, and this parses those and passes them on to the internal COF linker, which uses the Microsoft style arguments. When his patch was upstream, it was possible to build and do some things with these tools entirely with upstream code, with no outside patches required anywhere. So that was a turning point for the project, because from that point on, I set a policy that I'm not going to maintain any patches out of tree. These things need to go upstream because I don't want to be the one carrying this patch set forever. And I didn't really set out to maintain a toolchain. This started out as a branch on the VLC repo called Docker BuildBots, where they were building different toolchains that they use. But building this turned out to be a slight bit more complicated than you wanted to. So I split it out as a separate repo, and I call it llvm-mingw by the end of 2017, as a reference example of how do you manage to put these things together. So with a toolchain, entirely validated on Wine, no real OS scene, I talked to my friends at Videoland, and they talked to their friends or acquaintances at Microsoft and said that, you know, what's up? So they managed to get me a prototype device by the end of 2017. Prototype device running an OS which is not public or anything. Well, I could try my toolchain. Did it work? Of course it didn't. I mean, who am I kidding? No, it didn't work. But it wasn't actually too far off. It was almost there. There were only 3 issues remaining. So the first one, giving you the error dialog that you saw on the previous page, was that Windows on ARM64 refuses to load binary without the dynamic base set flag set. Well, that's just toggling 1 bit. Ta-da! Now it runs my executables. Then I was able to run small trivial executables. If I had something bigger, allocating a bit more stack, it was crashing. So then I had to sit down, figure out what's going wrong. Then I learned about stack probing. I learned this the hard way on the real OS where it's crashing. If I'm running on Wine, it's allocated, at least at that time, had allocated a big stack for me, and I didn't need to do any stack probing. Then it turned out that setjump from the UCRT or MSUCRT didn't really work for me because they require you to have SEH unwind information. And it turns out if you're building a GUI with a Qt and free type, they are actually allocating a small amount of memory, try to see, can I render my fonts into this? If it was too small, then we long jump back and allocate a bit more and start over. So to have a usable GUI, need to fix setjump and long jump, and that's quite trivial to, it's just dumping a couple of registers. It's quite trivial to provide yourself. So with that in place, I managed to port and have VLC building and running in 2 weeks. The toolchain itself was quite immature though, so it wasn't it wasn't pretty, and I had to fix both a lot of code issues on VLC side, doing assumptions, and also working around things that were missing in my toolchain. So then the next spring, on the MS Build conference in 2018, let's see if this worked. So at the MS Build conference, they were unveiling that Windows on ARM64 is a thing, and now you can develop for it. And let's see if you can hear the sound from this thing. So to showcase this,
I'm thinking, VPN driver, it looks simple. I just saw like 5 C files, I saw like 5 header files. That sounds like very simple. What about a more complicated app? So we reached out to VLC. VLC, I don't know if you know, is one of the most commonly used software on Windows. It's a media player, right? It's open source and it's extremely popular. We know that based on our usage, right? So we reached out to VLC and we were like, hey, are you interested in porting your app, your desktop app to ARM64? And so Jeff Baptiste, who's the main developer from VLC, he was like, yes, we're in, we're keen, let's try this out. And so we shipped him a couple of devices, right? We loaded them up with Windows, we gave them preview tools, and in shockingly short order of time, they have this up and running. In fact, we have folks from VLC in the room. I don't know if Hugo is here. Maybe, oh, there he is. There's Hugo. So he's from VLC. So if you do actually have questions on what they did, you should reach out to him. Again, just to belabor the point, when I asked John Baptiste, like, how much code did he have to change? His answer, 0. He changed 0 lines of code. His biggest problem was, again, VLC has its own homebrew way of building things. And so ingesting the latest Visual Studio Preview compiler into his build system, that was his biggest challenge. Changing code, 0. He didn't have to change a single line of code. Everything just worked. So let's.
yeah. So, I mean, that's partially true. Jean-Baptiste didn't change any lines of code. I did. And I mean, I had 60, 70 patches or something on top of VLC to make this work. And they wanted to sell that, yeah, this is so easy to recompile your app if it happens to use MSVC from before, but it didn't. So my conclusion was that it's actually more attractive to develop an entirely new toolchain from scratch, including everything for that, than to switch your build over to MSVC. But anyway, so back in these days, the toolchain, it worked, but it wasn't pretty. I can admit some of my wrongdoings or like my hacks that I used to do. So we didn't have any strip tool or object copy or strip to remove debug information. So either you build your linker executable without debug information, or it will live with you forever. But we could take the strip tool from GNU tools, from WinUtils, and use that. But it doesn't recognize anything but the x86 binaries. So we just do a small wrapper around it to change the architecture flag for the binary to x86, pass it to GNU WinUtils to strip, and then set the right architecture back. This works. It's not pretty, but it works. Let's ship it. So at some point, implemented an actual object copy tool in LLVM, or implemented PECOF support for that. Worked a bit on the LLVM resource compiler, so I didn't need to have a wrapper around that for doing pre-processing and these kind of things. So the project grew up and has matured quite a lot since then. For being able to actually compile most of the existing libraries and projects that run on MinGW, maybe the biggest feature to implement was, not biggest, but most important one, was the auto-import and runtime pseudo-relocation support, where you can reference data in another DLL without having to declare it as DLL import, which many libraries that are designed just on Unix and ported to Windows with MinGW rely on this. And technically, it's quite an ugly mess, but I implemented it, and then lots of things worked. I have gotten rid of lots of these ugly quirks in the build process, but then thanks to ARM64EC, I'm adding new quirks in the build process again. Thank you for that. Initially, this was entirely just a cross-compiler, so you run it on Linux and you produce binaries that will run on some foreign platform from somewhere. But then it turns out that some people actually want to run the compiler on this foreign platform somewhere else, so I need to build it for that as well. And as this initially was quite strange setup that some people played with, now it's quite a mainstream thing. Others do the same. So the MSys2 ecosystem has got their Clang64 environment, which is set up in exactly the same way. And they have built 3,447 packages out of 3,500 successfully in this setup as well. So my job is done here, or is it? So the issue is that once you've done something and made it work, there's a risk that somebody else goes and breaks it. And that doesn't make me very happy, does it? So the issue is that LLVM evolves at an absolutely furious pace. There are 100 to 150 commits every single day. There are 2 major releases per year, 6 months apart, and there are around 19,000 commits happening in between. And I will tell you, some of those 19,000 commits will break your setup somehow. Any commit can introduce it, and the issue is that it's quite easy to see that, yeah, you're touching this area, it's going to break something here. But in a compiler, there's quite a lot of the butterfly effect. You're touching code somewhere, trying to tweak vectorization for x86, and it breaks my ARM output somehow, because the compiler does a series of passes, transformations, and if you're changing things, so you hit a pattern that you weren't hitting before, then a later pass can end up doing something which wasn't really tested, and so on, hitting lots of bugs. So how do we avoid bugs? We can stick to stable releases and hope that somebody else has caught the bug and fixed it before I look at it. This is quite a viable strategy. I mean, most of you do this. But the issue is that if you're targeting MinGW, there's not so many others who are actually testing this regularly. So if the bug is only affecting MinGW or only affecting Windows, then the risk is that the bugs go unnoticed until I want to make a release, and then it's kind of late. There's also lots of small breakages that are reverted like within a day or so. So LLVM has got this quite wonderful policy that if you break something, if something is broken by somebody's commit, it's okay to just push a revert. We figure out what was wrong, if it even was wrong. It's totally okay to revert an entirely okay patch if it's urgent for you while you figure it out, because you have so many working continuously, simultaneously on the same repo. And if there's a bug that's crashing for me, it's kind of bad to leave it in the code base while we discuss it. So everybody else also are going to run into it, and they also have to debug it. So revert first, think about how to fix it later. So for me to test my compiler, I continuously test the latest Git. And I test the use cases that are important for me, that somebody else probably isn't. Anything that I've set up, or ideally, anything that I've set up at some point, I keep testing continuously to make sure that it works. And as an example, the Chromium team also are using Git snapshots of LLVM. They try to update it every 4 weeks or so. And if you have a complete enough set of tests, and if your new compiler passes all the tests, everything is good, then that's your new compiler. There's nothing more to it, which is, of course, good if you have good tests. So a bit of explanation also on how does LLVM itself test things. It's not what you might expect. It's quite a lot centered around small, narrow unit tests. Every time you do a functional change to any component, you will need to have an accompanying test. So if something was broken and you fix it, then you add a test. Every time, add a test. And the tests are like you have a small assembly snippet. Assemble this and check that the output file has the properties that we're interested in. We're not looking to diff the output file bit by bit to make sure that it's identical, because that would break all the time. But if I'm doing this transformation, if I'm assembling this construct, does it produce the right output, and so on. So the tests are not, the code that you're compiling in the test is not executed. I can run the tests on Linux and PowerPC and still validate that if I'm assembling things for Windows and ARM64, the output is still the one that I'm expecting. Which is good in one sense. You have really good test coverage of the tools themselves, while you can run 50,000 tests and you still don't know, does this produce a working executable? So to actually know that it works, you still need to do the higher level tests as well somehow. LLVM has a bigger test suite of other things, but it doesn't really support Windows, and I'm not sure how much extra test coverage it actually gives. So when you're updating to a new version of LLVM, what can break? Well, essentially anything, but let's look at a couple of different cases. One case is that last year I was able to build LLVM with my compiler on, say, Ubuntu 20.4. Now I no longer can't, because it's using some odd C++ construct or whatever. Another case can be that I can no longer build my favorite project with Clang, because Clang says that my code has an error. Well, if Clang says that your code has an error, then go home and fix it. Basically, it can of course be a bug. Then you go, if you think your code is right, then you go talk to the guy who made the new diagnostic. Then we have the problematic case of my code builds fine, but it no longer does what it's supposed to. If your code has undefined behavior, then that's on you. You go home and fix it. If your code doesn't have undefined behavior and it's still broke by the compiler, then there's probably some code generation bug in there, and you need to look into it. And the sooner you catch it, the better. The first step at this point is to try to bisect down which commit in LLVM changed things so it broke. If you're doing this nightly, then you have 1 day worth of commits, 100, 200, 150 to bisect through. That's not too bad. If you realize it after half a year, then it's 19,000 commits to bisect. It might be a bit more work. Well, actually not that much more, but still. Then we have the last category of things using Windows-specific APIs and such differently. So that you might need to actually test on Windows, but these kind of things don't really break that much, that often, and they don't really break accidentally. Like if you're changing code on what Windows API do I call here, then you know that you might need to want to check that it works on all versions in the same way. But the main takeaway is that the biggest category of issues above, the miscompilations, they're quite easy to test in an entirely Windows-less environment. You can test things quite well with Wine by running, for example, as I'm involved with FFmpeg, their so-called fate tests. They decode a lot of samples and check that the output is it has something like 5,000 tests, and this finds issues quite often. Still, things aren't that bad. If you compile LLVM with asserts enabled, then you can catch many of these issues already at the build time. So the assert will fire and say that things seem inconsistent, and the compiler gives up. So that's quite easy. You can't argue with that. Yesterday the compiler was fine. Today it's hitting an assert. Then whoever changed the code, talk to them and say that your change is wrong, and you push it revert. So the takeaway of this is that if you're using an unproven git snapshot of LLVM, you really do want to have asserts enabled. It will make the compiler 30% slower-ish and so on, but it's well worth it once you hit a bug. Then you have the even much more annoying case of bugs that don't hit an assert. It just does the wrong thing. So then you need to actually pull up your sleeves and sit down and try to figure out what's wrong. So the first step I usually do is take the pre-processed output of compiling the source file. So I don't need to build it with all the libraries, all the includes and so on, but I get one pre-processed file which you can compile anywhere. Then I can give this file to the other developers and say compile it with these flags and look at the output. You can also use a tool called cvice or c-reduce to minimize the reproducer. So if you're still hitting like an assert, then you can have an interestingness test which checks that if I'm compiling this file, do I still hit the same assert? And this tool can automatically try to reduce the code, removing unused parts and so on, and try to run it until you have the minimal source code which still is hitting the same bug, which is quite usable. So originally you have a big file of a couple hundred kilobytes or megabytes of pre-processed code, and you get it down to 5 to 10 lines reproducer, which is much nicer to give to somebody else. Say that these 5 lines of code trigger the assert, please fix. But then for the issues that don't trigger asserts, you find out which is the offending object file. So if you compile everything with the old compiler and just one object file with the new compiler and things crash, which is the object file? Then you try to pinpoint what's actually wrong. You can take the assembler output with a good compiler and the bad compiler, diff it, look at the diff, see if you can figure it out, and tell the guy who's caused it. So that's about what you do about that. But then the other practicalities of it. So testing LLVM, building LLVM is something which takes a long time. Anybody who's touched it is probably quite familiar with this. It takes a really long time. So for people involved with wine,
very fast on the arm.
yeah, it is. It's quite nice on that one, but still, compared to other things I compile, it takes a long time. So I measured, compared to wine, compiling LLVM takes 4 to 6 times as long, depending on which project you enable. If you have a fast modern machine like this laptop, it takes 15 minutes. If you have an old desktop x86 machine that I used to have, it will take over 2 hours. The same thing on GitHub Actions. And the other issue is that since there's so many commits every day, it means that if you're compiling once a day, somebody has almost every day touched some enough files that you end up recompiling essentially every single file, or at least the vast majority of it. And it's not just like once a day, but if you're updating continuously compiling, you end up recompiling everything probably like 3 to 5 to 7 times a day. So this just sitting down and compiling on a fast machine will take hours a day. So how do you do quality assurance of this on the zero budget, as I had the heading? So I do test these things, compiling the toolchain on Linux and running my test executables with Wine. I used to do this with an old 2011 desktop Linux machine. It was a cheap machine back then, and it wasn't really fast. But the point is that you can do this with like essentially no resources at all. Even a slow machine can build this overnight and run quite a bit of tests. And I used an old 2015 ARM dev board to run the ARM tests. So compiling things on x86 and then copying files over to the dev board and running those tests over there. Well, this isn't the whole truth, because the old machine actually finally died last year. I bought a new one, and that one's actually fast. So that's much nicer. And also in 2021, I got a free 4-core ARM64 server from Oracle Cloud, which also isn't fast, but it's free, and it's available 24/7. So it was kind of as fast or slow as my old x86 desktop machine. Compiling LLVM takes around 2 hours and so on, but still I can do it nightly and it gets done. And it's much nicer to run than an old ARM dev board, which is quite flaky at times. So I build all these things nightly. I pull down the latest LLVM, build that with the latest MinGW. I run a small set of smoke tests to see that if it's fatally broken, just ditch it and leave it there. If the smoke tests are fine, then we install it that this is my latest nightly compiler and use this. With the old hardware, this took a bit over 2 hours. With the new machine, 20 minutes. And then I use this toolchain to try to build most of the open source projects that I'm involved with. So first off, build VLC. I built the latest VLC from Git. I'm not using a known good snapshot because using a known good snapshot would be easier find if there's an actual bug in the compiler itself. But on the other hand, then I don't know if the latest version compiles. So it leaves me a bit more testing. If something breaks, was it a VLC change or an LLVM change that broke things? But that's still better than doing it the other way around. With my old machine, compiling this took 2.5 hours. With the new one, 15 minutes. But here's the practical trade-off. So if it takes 2.5 hours to build this, I'm not going to build all 4 architectures that I care about. I build one architecture per night, and I wrote it through this. So if there's something that's broken in an architecture independently, then I find out the next day. If something breaks for one specific architecture, I will find out within 4 days. And that's still quite reasonable. I don't try to run any tests with it. I just build it and store a package with a date and timestamp. So if there's something that turns out to be broken later on, I can dig into my archives and dig up the old date tagged snapshots and see at which point did things break. I build ffmpeg and run their tests on all 4 architectures. I run the tests with Wine entirely on Linux. Originally, I compiled everything on x86 and ran the ARM tests on the small dev board. This was quite slow by the end when they had added more tests. So at that time, running the whole set of tests on ARM was an hour maybe. Now I run that on the free Oracle server. I build a bunch of other projects, Qt, x264, David, OpenH264, and so on. It's probably all just gibberish if you're not into multimedia. The latest addition to this is that I built the latest Wine on all 4 architectures. I built most of the configurations, so I built both the ELF-based ones, PE ones, and also the new Windows on Windows 64 setup where applicable. I build all of them each day, but then I pick one of them as the one that I'm installing for use each day. So if there's something broken in actual use on one of the configurations, I might find it within 3 days. If it's broken everywhere, I find it the next day. If it breaks compilation, I find it the next day. I wrote it between compilers, and if I'm compiling the PE stuff in llvm-mingw or MSVC mode, again, to find any breakage within a couple of days. If the build is successful, install it and use it. And I use this for running to test compiling ffmpeg with MSVC wrapped in Wine. So this is also a configuration that I've set up and I've used, and I wanted to keep working. So I did a similar presentation a couple of years ago, and then I had looked at the statistics of, under the previous topic of Hauge statistics that we present here today. So I looked at the logs of build breakages from 2023 for a period of 173 days. llvm had progressed by 18,000, almost 19,000 commits, and building llvm and the MingW runtimes was broken 11 times during this. It could, of course, have been broken many more times, but by the time I built it nightly, it was broken only 11 times. There were 9 different code generation bugs that hit asserts. There were 2 cases of code generation bugs that didn't hit any assert, requiring actually to look at the code. And llvm bugs that produce a crash instead of the wrong output was once. Which means that if you pick a random snapshot of llvm, it's going to be good enough 87% of the time. I mean, this is a wildly inaccurate number, but it's still like a ballpark number. It means that, yes, things break. Usually, if you pick one randomly, it's probably going to be okay. So with my testing, with everything, with Wine, building and running these projects on Wine on Linux, I have quite a good test coverage. But there are still some tests that I might not have covered there. So it used to be the case that before a release, I fire up a Windows virtual machine and try to run a couple of tests. Test LLDB, test that I set the breakpoint, check that do I hit the breakpoint, do I get the working backtrace from there, run address sanitizer, see that does it detect overwrites as it's supposed to, and so on. just a basic set of extra smoke tests that need to run on real windows. I'm hearing that things might actually be working in wine with address sanitizer these days as well, but I haven't really tried that out. But the takeaway is that there are things that you might need to run on Windows, and I used to do it manually, and it's boring, and I forget or put it off. So things have progressed a bit more from there. There's also the case that libc++ in LLVM has taken a very hardline stance that if you are supposed to be considered a supported platform, you need to be in their pre-merge CI. If you're not in the pre-merge CI, then we consider you unsupported, and they don't say that they outright will go and break your code and they won't remove your code, but they make no guarantees about even caring about your patch, essentially. So it used to be the case that libc+ had tests running on Windows and they used to be passing at some point, but this had been not running for a couple of years, so it was quite badly bit rotten by the time I looked at it. There were hundreds of tests failing. Quite a lot of work to sift through them, figure out how to fix it or how to annotate it, that this is broken, we know it because of this, and so on. But after fixing that up, Google had contributed some buildables for LLVM itself running Windows that I reused for running the libc+ tests, so we could declare it a supported platform. And if they had buildbots running that I could also inject installing llvm-mingw over there and declare that mingw is also a supported platform. And this is quite useful actually because it has found and diagnosed a handful of bugs in mingw CRT as well. So later on, GitHub Actions came along and they provide free CI runners. And they are slow, but they are free. And the other big game changer there is that they have stuff running on macOS and Windows. I have a bunch of machines running Linux, unattended and so on, but I don't have that many unattended Macs and Windows machines. So you can run things there on GitHub Actions and you can script it, which is really, really valuable. And the recent development is that since this year, they also have ARM Linux and ARM Windows runners. So on the GitHub Actions, I set up building things the way I do locally, build all the release configurations and so on, and run some tests on it. And I could hook up the LLVB and address sanitizer smoke test there as well. So I don't need to test things manually except on ARM. And then came this year when they added ARM runners, so we can also run all the ARM tests there, which means that I don't have anything I need to test manually anymore, at least for a little while. Then the runners were updated with the latest version of Windows, where they dropped 32-bit ARM, so that's untested again, unless I test it manually. So the takeaway of this is that GitHub Actions is really valuable for running the actual tests on Windows, and you have an immense amount of CPU time you can use for building things. So as an example, this is what my build matrix used to look like. This is running nightly, or used to be running nightly. This is the simple version. So we build toolchains on Linux, on macOS, also test on Nemesis just to check that it's still working. With the Linux-based toolchain, cross-compile toolchain that will run on Windows, run a bit of FFmpeg tests, and then test those toolchains, run a bunch of tests over there. So you would hope that that would be it, but unfortunately things are even more complicated because there's one thing called PGO, Profile Guided Optimization, which works like that. So you build the application that you're interested in with the instrumentation. You run the instrumented build of your application, doing some sample tasks with it. So you get a profile of which functions are called, which aren't, and so on. And then you rebuild your application, you give the profile to the compiler, which can then optimize based on the knowledge of what's actually used and so on. So this sounds simple in theory. Let's apply it to a compiler. So the thing is, if you build a Clang with PGO, it can be 50% faster. If I ask anybody of you, do you want a 50% faster compiler, then hell yes, of course I want to. But it's not so simple to actually produce. So the first step, first we build Clang with the existing host compiler, might be GCC on Linux. In theory, we wouldn't need this step. We could use an existing host compiler as well, but for other reasons we do this. Then we're using this stage 1 compiler to rebuild Clang again with instrumentation. Then we use this Clang to try building things for all the 4 target architectures to get a profile of what parts of the compiler are actually used. And then we rebuild Clang once again with the stage 1 compiler with the profile that we just got. And as I might have mentioned, compiling llvm is slow, and here we do it 3 times. Hooray! So how does this fit into my build setup? First off, it requires 3 times the amount of compilation effort. It's painful already to begin with. I don't want to do it 3 times. I'm providing 10 different release packages. Do I want to do all this effort for all these 10 packages? The second thing is my build procedure is very much set up with cross-compilation in mind. I'm building toolchains that will run on Windows on ARM64 or Windows whatever, but the basic premise is that while building these toolchains, it's not possible to actually execute code for this target architecture. So you can't really run the profiling and instrumentation stages because you're cross-compiling things for an architecture. So the solution for this is that we only profile once on Linux and use the same profile for all the target builds. There's lots of small details in this. You can do it in many different ways, but the key takeaway is that you don't get the full 50% speed up from it, but by using a slightly simpler profile and reusing it for a different target architecture, you can get up to 30% speed up across the board. You don't get 50, but the cost is tolerable, and you don't need to build everything 3 times. You just build llvm 2 or 3 times extra. The other complication is that if you're building things this way, if you actually have a bug in the compiler, it becomes really annoying to debug. So if you don't build things this way, you can pretty much assume that the host compiler you're using is in the cost, but if there's a bug, it's in the code. If it's crashing at location A, you look for a bug in location A. But if you have your compiler built this way, if you have a crash in location A in your compiler, it could be that you have a functional code bug somewhere around that area that's causing the crash. It could also be that the issue is not at all in that area. The issue is in the previous copy of Clang in a different file, which is just causing file A to be miscompiled. So if you have to bisect these things, you kind of need to have a separate set of sources for the different stages to pinpoint which one of these is actually causing the issue. So with this implemented, this is what my nightly builds look like these days. First we build the first stage, then we build a profile with that, and then we use the profile for rebuilding all the target builds there, and then we run the tests. Previously, this ran in 6 hours something. Now it's back up to a bit over 8 hours again, but it's free CI resources. So that was all that I had.
Thank you.
Yeah. So the question is, why did my old Linux desktop stop working? The hard drive died.
What part of it?
I don't know, but it was giving read errors and slowly becoming unreliable. Yep.
Have you find some kind of non-deterministic error, like if you run the compiler once, you get the same conditions?
So there's a question of have I found any non-deterministic cases where the compiler produces a different output each time? I don't think I've actually hit that bug. Or yeah, in some cases, if you have, oh yes, there have been these cases as well, and they are even more annoying to debug. Yeah, it's not very common, but they do happen. Yeah.
First of all, very good job.
Yep.
And a lot of effort. Wow. If you do something special to get this free Oracle course, because I once tried a couple of times, and they refused me every time.
So that's a question of what did I do anything special to get the pre-ARM, the Oracle servers? And no, I didn't do anything special with that. I heard about this, I think I read about it on Hacker News in 2021, and I signed up and I just get a slot. But the thing is that if you shut down the server, you might not get it started again because there's many others who want to, like, they have a separate set of hardware allocated for the free users. And if you shut your down and somebody else powers up and gets your slot, then you lost it, and then you need to wait and retry until somebody else shuts down their server.
It felt more like they refused me in person.
Oh, okay, well that might be something personal about you.
personal.
They've been clearing dormant accounts off. So a number of cores that they reserve in each of the regions might be starting to open and pretend to be somebody else. Because you look.
What was your name?
Thank you very much.
Thank you.